Hello, everyone. My name is Jonathan Baugh. I'm at the University of Waterloo and the Institute for Quantum Computing. I'd like to thank the organizers for inviting me to give the talk today. And I'd like to talk about semiconductor nano-electronics for quantum information and sensing. I'm just going to turn off my video for the rest of the talk. I just wanted to show my face there at the beginning. Okay, so so in my group, we work on a few different research topics. This is not an exhaustive list, but this is a few of the main things that we've worked on the past few years. In this talk, I'm going to focus on just two of these topics. So the first one will be carbon nanotube, nano-electro-mechanical devices based on suspended carbon nanotubes. And the second topic will be on electron spin qubits for future quantum computers based on silicon, metal oxide semiconductor devices, and an architecture that we propose for scaling up. So we've also done some work with single electron devices in undoped gallium arsenide, and we're also working on single hole devices. And we've also done some work with superconductor-semiconductor hybrid devices, studying the Andreev transport physics there. But I just don't have time to talk about all of that today. So let me start by talking about nanoscale force sensing with CNTs. Suspended carbon nanotubes make really nice nanomechanical resonators for force and mass sensing. This is possible because, carbon's a light atom, and you don't have so many of them in a carbon nanotube, so the mass is very low, and yet mechanically you have very high rigidity. For these suspended devices, it's possible to obtain very high quality factors, from tens of thousands up to, around 1 million. And so combining the low mass, the high Q factor, the high rigidity, we can get very excellent force sensitivities. So, some other groups showed a few years ago some really beautiful results, being able to resolve, showing mass sensing at a resolution of a few atoms. So around 16 chromium atoms in 2008, and then individual xenon atoms binding to CNTs was resolved in 2012. So this is a really nice system for this kind of force sensing. So the idea that we had a few years back was to apply this to magnetic force sensing. So where we want to detect and measure individual nanomagnets. These could be single molecule magnets or some other sort of nanomagnetic object that's grafted to the carbon nanotube. So similar, conceptually to the Stern-Gerlach experiment, we can think about employing a strong magnetic field gradient to impart a magnetic force on this nanomagnetic object. And so, the device would look something like this. We have our suspended CNT over a gate. So far, that's just the standard suspended CNT transistor. But if we make that gate out of a ferromagnetic material, this could be nickel, iron, or some alloy like permalloy, then we can actually obtain quite a large magnetic field gradient felt by the nanomagnet on the CNT. If we apply an external field along the CNT axis, then the field gradient can reach values up to about 10 to the 5 Tesla per meter. So the question that we tried to answer in this theoretical paper back in 2014 was, can we detect single molecule magnets? And the answer is that in principle, yes, we should be able to. We should be able to resolve the shifts in mechanical frequency of the carbon nanotube due to the forces imparted on the single molecule. Now, of course, whether you can do that in practice depends on lots of caveats having to do with the real properties of the real device. Okay, but at least that was our motivation in studying these kinds of suspended CNTs. So experimentally, this is how we make these devices. These days, we've tried a few different methods, but most reliable method seems to be the stamping one, where we grow the suspended CNT across quartz pillars using a CVD growth method, and then we take those CNTs on quartz and we stamp them onto a device substrate that has predefined contacts. Okay, of course, we're doing this in an array, and so you only have a yield of maybe some percentage of devices actually end up having suspended nanotubes, but the ones that do tend to work well. This is just a picture of one of our device chips before it goes into the cryostat. This is one of the cryostats that we use to do measurements. This happens to be a 1.5 Kelvin pumped helium cryostat. I'll also show some data from a dilution refrigerator. And then this is a typical IV, I versus VG transconductance trace showing Coulomb oscillations both on the electron side and on the hole side. So typically here we're interested in semiconducting CNTs with relatively small band gaps. Right? So here you can see the band gap between the electron and the hole side. And I should say that all of this work was the PhD project of my former PhD student, Kyle Willick. So I'm give him the credit for actually doing all this work. So, if you zoom in on those Coulomb oscillations and you look at them as a function of the bias, the source drain voltage, then you would see these, this regular pattern of so-called Coulomb diamonds. And, anybody who studied quantum dots knows that that's the standard, pattern for conductance of a single quantum dot. So what's happening is that the suspended section of the carbon nanotube is acting like a quantum dot. Electrons can tunnel on and off the nanotube at the contacts, and between those tunnel contacts, you have a dot. And because there's a charging energy required to add an additional electron to the dot, then you get these Coulomb peaks and Coulomb diamonds. So within each Coulomb diamond, you have zero conductance, and you have a fixed number of electrons on the dot or on the CNT. So, this gives you sharp peaks in conductance near zero bias, and we're actually going to exploit that when we measure the mechanical behavior of these devices. Just as a side note, you can also see clearly excited orbital states in this data on an energy scale of about 1 millielectron volt compared to the charging energy of about 8 millielectron volts, typically. Okay, so we use this method of Coulomb rectification in order to see the mechanical resonance, measure the mechanical resonance frequency of the suspended CNT. So, the idea is that as the CNT moves up and down, it's going to modulate very slightly the gate capacitance. And through that modulation of gate capacitance, you get a modulation of or an effect, actually in this case a DC effect on the current, if you happen to be measuring on one of these Coulomb peaks, on the side or the edge of one of these Coulomb peaks. So in other words, if you have a nonlinear feature in the conductance, then you can exploit that nonlinearity to see the mechanical resonance. What that really means in practice is that you start with this Coulomb peak. When you're driving the CNT onto its mechanical resonance, what happens is that peak broadens. And so at the center of the peak, the current decreases noticeably. And in the wings, the outer parts of the peak, the current increases. And so that's exactly what we see here. Here we're showing some real data that we measured. This vertical red feature is a Coulomb peak. And when we hit the mechanical resonance, you can see this sort of V-shaped signal that's appearing. And so you can see that what's happening at the top of the Coulomb peak is that the current is reduced, and outside, and on the outer edges of the peak, the current is enhanced. So exactly like this diagram I'm showing here. We can also see that the mechanical frequency dips a little bit on top of the Coulomb peak, right? Because on the vertical axis here, we're plotting the frequency. And the reason that happens is because, on the Coulomb peak, you have electrons tunneling on and off the CNT at a high rate. And so that changes the stiffness of the nanotube, and therefore it changes the resonance frequency. Okay. So we sweep an AC drive frequency, and then we can see when this resonance occurs. Now we can measure that resonance frequency, that mechanical resonance frequency, as a function of the gate voltage. And so that's what we're plotting here. And we actually fit this data to a model based on an Euler-Bernoulli beam model of the mechanical resonator. And it, as you can see, it fits quite well. Now we can also combine this data with axial field magnetospectroscopy. So there we're looking at the coupling of the orbital angular momentum of electrons circulating around the nanotube to an axial magnetic field, and how strongly those energy levels shift with a magnetic field tells you something about the diameter of the carbon nanotube. So we can combine the previous data of resonance frequency versus gate voltage together with this magnetospectroscopy data, and we can get good independent but agreeing estimates for the CNT diameter. So typically for these devices, we're looking at about 2 nanometer CNTs. With our devices, the suspended length is about 2 microns. We can estimate a lower bound to the Q factor from the mechanical line width, and that's about 20,000 for our devices. That's really a lower bound. We can't really measure the true Q factor. We can only, technically the way the measurement is done, we really only see a lower bound there. And our devices tend to be, these stamped devices tend to show residual compression rather than residual tension. Okay, so so far, I should say that we haven't been successful in detecting nanomagnetic signatures on these CNTs, and I think that has actually a lot to do with the chemistry of grafting molecules to the CNT properly, and having the molecules remain intact through that process. But with these devices, we have made some interesting observations, and I'll just tell you about one of those here, one of our recent observations. And this has to do with self-driven or feedback-driven mechanical oscillations. So, if we go back to, if I just go back quickly to these Coulomb diamonds that I showed you earlier, these regions inside the diamond should have zero current, because the conductance is zero there due to the Coulomb repulsion of electrons, right? So electrons are prevented from tunneling on the dot due to Coulomb repulsion. That makes the conductance and the current zero. But what we observed in some of our devices when we cool down to very low temperatures, without any mechanical driving, without any external driving, we see very significant current appearing within the diamonds. And so it took some time to think about what was happening, but eventually we realized that this can only come from having large amplitude, so amplitudes on the order of a few nanometers of mechanical oscillation. So you can see that in exactly the same device, you see these very obvious signatures at low temperatures below 100 millikelvin. But above 1 Kelvin, you don't see them. Now, you do see some signatures that are still connected with self-driven oscillations, but you no longer see current within the diamonds. So, what's going on here? What is the mechanism? So we wanted to clarify this. So what we did is we came up with a theoretical model, and we found that negative damping can occur in association with a charge state transition, meaning one of these Coulomb peaks, for certain types of energy-dependent tunneling. So in other words, when the tunnel rates vary in certain nonlinear ways with the energy, right, with the Fermi energy. So what happens is that small amplitude motion can be amplified near one of these transitions and in a feedback loop. And so what I'm plotting down here is the two edges of charge transition and the damping parameter gamma as a function of the chemical potential. And what we see is that, as we would expect, gamma is positive, at the edge of the charge transition. But if we have a certain kind of energy dependence to the tunnel rates, it's possible for gamma to actually be negative in this region between these two edges. And so what happens is if we tune the device to a configuration near one of these edges, and there's a small amplitude oscillation due to thermal effects or maybe some spurious driving, then that can be, if that overlaps with this negative damping region, then the oscillation can be greatly amplified until it reaches some, maximum value. And once those oscillations are present, they manifest as this additional current within the diamonds. So I won't go into the technical details of this model because it is a bit involved, but it's a master equation model based on some straightforward assumptions. And we can see here that the model gives actually quite good qualitative match to the observations. So this panel up here is the experiment. This panel here is predicted from the model. And not only does it explain pretty well the observed dependencies on voltage, but it also agrees qualitatively pretty well with the temperature dependence that we observe as well. Okay, so just to kind of finish off this part, so we have a paper on this self-driven oscillation that just came out this year, and the two previous papers that I mentioned earlier are here in case you're interested in reading more about that. And just one final note, I didn't really go into it, but on the whole transport side, we also see some really nice physics. So when we look at the conductance map on the whole side, we see this fourfold shell filling, which is a well-known feature for both electrons and holes in carbon nanotubes. But we also see these interesting features near zero bias, which are due to Kondo-enhanced transport. So there's a strong Kondo effect here for the holes, which we actually didn't see for the electrons in these devices. So this is just to say that these suspended devices are mechanically nice with high Q factors, but they're also electronically pretty clean devices. And there's a lot more that we could explore there. Okay, so in this second part, I want to talk about quantum computing in silicon. And to do that, let me first present some context around quantum computing itself. So as you may know, this is predicted, quantum technologies in general are predicted to be a multi-billion-dollar industry over the next few decades. So quantum computing promises to bring us efficient simulation of quantum systems, which can have really important applications in quantum chemistry, drug design, biology, and so forth, medicine. There are a number of computational problems that we know quantum computers give an exponential speed up to. There are some where we have a quadratic speed up, like database searches. Recently, algorithms have been discovered for solving linear systems with a significant speed up over conventional algorithms. And going beyond the large-scale quantum computer, there are many other aspects to quantum technology that are important, like long-distance quantum communication, special purpose simulators of physics and chemistry and so forth, and as well as quantum sensing. And there are lots of different flavors of quantum sensors starting to appear. Now, of course, the challenge for all these quantum technologies is decoherence, right? You define a quantum bit or a qubit, and you realize it in some physical system, but interaction with the outside world is unavoidable. And quantum coherence is lost on timescales, which we typically call T1, which is the energy relaxation timescale, and T2, which is the dephasing timescale. So decoherence reduces a qubit to a classical bit, and then, of course, you've lost the whole quantum advantage. We can define a quality factor for a qubit, which is just the ratio of the dephasing or decoherence time to the timescale of an operation, a quantum operation, like a quantum logic gate. And if Q is greater than or equal to about 1,000, then we could call that a good qubit, or a qubit that could be practically usable. Now, this problem of decoherence, the way that we get around it in theory is to use quantum error correction. There are many flavors of quantum error correction out there. The one that's probably the most practical and that applies directly to any device that's any devices in a planar configuration, sort of a 2D planar device configuration, is called the surface code. Or, well, there's really a family of these surface codes. This code provides one of the highest error thresholds of any code, close to 1%. So in other words, it can tolerate errors in quantum logic gates close to 1%. It has a 2D topology which matches nicely to devices that we can actually fabricate, and the size of the code can be adjusted to match the actual error rates. So it gives you it optimizes the use of resources. Now, like most other error correction codes, this one requires repeated measurements and feed-forward corrections. So you're continually performing measurements and using that information to update future operations on the processor. Now, the type of qubit that we're interested in is an electron spin that's confined to a quantum dot. So electron or hole spins in semiconductors are promising qubits. And in particular, silicon is interesting because we can isotopically remove the nuclear spins. So, that's one of the problems with 3-5 semiconductors like gallium arsenide, is that you cannot remove the nuclear spins. There are no nuclear spin-free isotopes available for those compounds. And so that presents a really big noise source for the electron spins that produces the nuclear spins produce magnetic noise. But in silicon, we can remove the nuclear spins by using 28 silicon, and therefore we can create sort of a magnetic vacuum in which electron spin qubits can have much longer coherence times. And this is something that's been shown experimentally to be the case. So the idea is that we make a device that looks something like a CMOS transistor, except that what we're really doing is creating a little island of charge called a quantum dot, and we can tune it down to the last electron or the last hole, and we can use the spin of that particle to represent a qubit. Okay, we can perform gate operations by using electron spin resonance to rotate the qubit and perform what's called a single qubit logic gate. Or we can use the exchange interaction between electrons in neighboring dots by manipulating the tunnel coupling between the two dots in order to perform 2-qubit logic. Okay, and so just to give you an idea of the state of the art, a 2-qubit device a couple of years ago by some other groups demonstrated all the operations necessary for a 2-qubit algorithm: initialization, manipulation, and readout. And the state-of-the-art gate fidelities that people can usually achieve in these devices these days is greater than 99% for single qubit operations and around 98% for 2-qubit operations. Okay, so this is very promising, and not only because we can remove the nuclear spins in silicon, but because we can take advantage of the vast infrastructure and knowledge around processing of CMOS devices. So the question becomes, how do we scale quantum dot spin qubits? So this is an SEM picture of a device that we've actually studied in our lab, that we fabricated and studied. And so, this is sort of at the 2-qubit level. Now, how do we take that and scale it up to something like a large-scale surface code with thousands or possibly even millions of qubits? That's the question. Well, people have proposed some ideas for this. So there was a CMOS architecture proposed back in 2016 that was really just trying to map, to create a 2D array of quantum dots that could easily be mapped to the surface code. But the practical challenge here is that quantum dots are very small, and so the interconnect density would be extremely challenging for such an architecture. A little bit later, another architecture was proposed that took advantage of being able to move electrons between adjacent dots, called shuttling, and this provides some advantages, but still has many of the same challenges. So what we've actually proposed is to use a distributed network approach. So as I said, quantum dots have the challenge that they're very compact. Of course, it's an advantage because it means that we can put many of them on chip, millions, perhaps even billions. And that's a nice property compared to some of the other quantum technologies like superconducting qubits, which tend to take up a lot more space. But it's also a challenge because they're so compact that it's hard to imagine 3D wiring necessary to get sufficient control over a close-packed 2D array. So we can actually, we don't have to build a close-packed 2D array. We can actually marry the idea of a monolithic chip and a network architecture where we have a network of nodes. Now, the only thing that we need to make that work is to have a scalable method of entanglement distribution. Okay? So we have these nodes where everything is done locally within the node, But if we can share entanglement between nodes, then we can map the 2D surface code. We can map the 2D surface code that we would have in this monolithic architecture to a network architecture. So essentially, we propose to split the scaling problem into two pieces, right? One where you have local node operations, and the other piece is to distribute entanglement between nodes, which allows you to do quantum operations between nodes. Now, this has the advantage that it would create space for realistic wiring densities. So you could spread these nodes out in order to accommodate the control wiring as well as control and readout electronics. This method can also tolerate rather large errors in entanglement distribution and even local gates if you use some additional resources for error correction or entanglement purification. So how would we do this with quantum dots? Well, there's a natural way to do it, which is that when you put two electrons into the same dot and you put them into the same ground orbital state, by the Pauli exclusion principle, they have to form a singlet. And of course, a singlet state is an entangled state in the basis of spin up and spin down. So we can prepare a local singlet, and then we can separate the two electrons by shuttling one electron through a sequence of empty dots to some non-local or just to some distant location. And then we have a non-local singlet as long as the spin is preserved by that transport. So we get entanglement for free, in a way, in quantum dots. And we're going to focus on this shuttling method as the way to distribute entanglement between nodes. Of course, there are other ways that you can think of, but we'll focus on shuttling here. So, as I mentioned, the scaling problem then really breaks into two pieces: few qubit nodes, which is something close to what we can already do with near-term technology, plus this ability to distribute entanglement over a few micron scale, which is perhaps a little bit more challenging, but we feel within reach within the next few years. Now, silicon is also promising from the point of view of this entanglement distribution, and that's because not only can we remove the nuclear spins, but the spin-orbit interaction is inherently weak in silicon. So it's not zero, but it's very small. And so that means that as we move an electron through the material, the perturbation on the spin will be very weak. And so we hope that, or we believe, optimistically that spin coherence can be preserved. And in fact, we've done some simulations and theory about that, but I don't have time to go into all that today. Now, experimentally, electron shuttling has been demonstrated very nicely by the Pettit group. They showed the transport of a single electron across 9 dots on a timescale of 50 nanoseconds. Okay, so this is very promising. This in this paper, they didn't say anything about spin fidelities, but in terms of charge fidelity, in terms of moving a charge from one place to the other, it has been demonstrated now in this work and subsequent works with very, very high fidelity, nearly 100%. So this is very encouraging. So we wrote a paper on this network architecture for a topological quantum computer in silicon. And so the idea is that, we have a node which is comprised of a data qubit, which is the main qubit that stores the important information. And then we have a few ancillary qubits that help during the processing steps. And each node is connected to a reservoir so that we can add or subtract electrons as we need from the dots in the node. And then we can distribute entanglement between the nodes by using what we call the shuttle highway. And this is really not too different from sort of like a CCD array. It's really just a series of elongated quantum dots, each dot formed by a single gate electrode that allows you to shuttle one electron or transport a single electron from one node to another node. Okay, and as I showed in the previous slide, that kind of transport can happen on the time scale of tens of nanoseconds. And so, the time scale for shuttling is not a bottleneck for this processor. In fact, some of the single qubit operations take longer than this shuttling operation. So in this paper, what we did is we really worked out exactly how you would map the 2D surface code to this architecture, and we showed that it could be done, and we did some theoretical estimates for how robust it would be to noise and errors. Okay. So finally, I just wanted to briefly mention about some of the experiments that we've done with these MOS dots. So the idea here is that we would like to simplify these devices as much as possible. So what I'm showing here is an SEM image looking from the top of a quantum dot. So here labeled P, the left contact L and the right contact R. And then in between them, you have a gap, and that's what forms the tunnel barrier. Now, what people normally do with these devices is you would put another layer you would put a dielectric insulator and then another layer of gates in order to tune the tunnel coupling directly with an additional gate. But what we're doing here is we're getting rid of that gate, and we're just using the geometry, using the gap, as well as the voltages applied to these remaining gates in order to tune the tunnel coupling. So in that way, we can reduce the number of electrical gates, the number of layers in the device, and hopefully make the whole thing more scalable. So what we showed in this paper is that we can, even with this very simplified geometry without explicit tunnel gates, we can still tune the tunnel rates over 8 orders of magnitude. Okay, so that's very nice. We were able to use this same type of device to look at spin filling through magnetospectroscopy. Okay, I won't go into all the details here because I'm probably running low on time, but not only can we see how the spins, how the electronic states get filled as you add 1 electron, 2 electrons, 3 electrons, but we can also get a direct measurement of what's called the valley splitting. And that's the splitting in the 2 lowest valley states in the conduction band of silicon. And that's actually a very important quantity to be able to measure from the point of view of quantum computing, because we always want to stay in the ground valley state. We don't want to be excited to the upper level valley state, because then we lose spin coherence. Okay? So this is just to show that we've been able to characterize the spin filling and the valley splitting of these devices. They're clean enough to do that. Even a standard MOS device is clean enough to do this. Okay. Now, of course, we can extend this to linear quantum dot arrays. Here I'm showing a double dot and the double dot charge stability diagram. And here I'm showing on the right a triple dot. And so the idea here, the future work that we would like to do in systems like this, is to demonstrate the shuttling and look at the spin coherence. So first of all, to show that we can indeed shuttle electrons without having these additional tunnel gates in this simplified geometry. And secondly, to quantify our ability to do coherent spin transport by shuttling. Okay, so just to summarize, in the first part, I told you about the carbon nanotube nano-electro-mechanical systems that enable ultrasensitive force detection, we proposed a magnetic force sensing using a ferromagnetic gate, and we've clarified the physics of self-driven oscillations, oscillations that develop due to electron tunneling processes on and off the CNT, and the fact that you can have feedback loops develop there. And that's an important thing to understand in these devices. In the second part, I've talked about electron spin qubits in silicon. We propose a novel network architecture that I believe is one of the best practical pathways to a scalable device. And I also told you about the few electrode device geometry, or the simplified device geometry, which we believe will simplify both processor nodes and shuttling circuits to improve the prospects for scalability of these devices. I'll just point you to our paper, Network Architecture for a Topological Quantum Computer in Silicon, which was published last year, if you'd like to see more details on that. And let me just very quickly get in a quick plug here. We have a review or roadmap paper on quantum technologies that should appear within the next few weeks in IOP Nanotechnology journal. This is a really nice roadmap paper. We have nearly 30 authors giving their perspectives on the future of quantum science and nanotechnology. So I think it fits in very well with the topics of this conference. And here I've just listed the topics that are covered in the roadmap paper. Okay, and with that, I think I will end the talk, and I thank everyone for their attention, and I look forward to answering any questions. Thank you.